In this video, we're going to take a look at how you can calculate binomial probabilities in problems that have a little more going on, where it's going to take two or more steps to work your way to the answer. The scenario we'll work with in all our examples is that you're going to guess your way through an eight question multiple choice test, and that each question has 4 choices. The random variable x represents the number of questions that you guess correctly. Here I have a quick recap of how I know that x is a binomial random variable. Freeze and take a look at that if you'd like a little more background. Here I've got the information on random variable x, the probability distribution function, along with the graph of that particular distribution function. Again, freeze and take a look at that if you want a little more detail. Let's move on to our first question. Let's find the probability that we're going to guess more than 3 questions correctly. Here I've got some graphs corresponding to this, and I've written in probability vocabulary, probability notation, what we're trying to find. It's the probability that a random variable x is more than 3. That's a little tricky up front because the binomial CDF function that we'll be using only finds probabilities below a given value. So what we're going to do is turn the problem around. Here I've got a graph of the probability I'm after. That's this red shaded area, the probability of getting 4, 5, 6, 7, or 8 questions right. To figure out that probability, I'm going to take the total area, so I've shaded everything as red, that's 1, and subtract the probability of getting 3 or fewer questions right. That's this shaded area. This is a probability that we can calculate using the binomial CDF function. So down here is where I'm going to actually do the math on that. N is 8. We're guessing 8 questions. There's 4 choices per question, so there's a 0.25 chance of getting any one question correct. And k is going to equal 3 because this is the probability that I'm going to find using the binomial CDF function. Remember on Excel, to get a binomial CDF, I'm going to type in equals binom dist, put in the value of k, comma, then the value of n, and then finally the value of p, and then tell Excel true to tell it that you do want a cumulative value. I'll press enter, and this 0.886 is the probability of these red bars up here. I want to find the probability of these red bars, so I'm going to take 1 minus that probability for my final answer. Equals 1 minus the probability we just found, enter. And we find the probability of getting more than 3 questions right is not very likely, about 11.4% chance, or a probability of 0.114. Notice this small number does correspond to the relatively small area of the red bars above here, so that's what makes me confident that I've actually worked this out right. It's good to do that double check at the end. Let's take a look at another problem, one that's kind of similar. Instead of x greater than 3, let's do a problem where we're finding x greater than or equal to 3. This time when we turn the problem around, we're going to take 1 minus the probability of the other shaded bars. The opposite of getting 3 or more isn't getting 3 or less, it's getting 2 or less, 2 or fewer. So when I calculate the CDF probability, I will not be using 3 as my magic number, I'll be using 2. That's why here I've got n, p, and k, where k is worked out as 2. Other than that, it's going to be very similar to the problem that we just worked out, binomial distribution of k, comma, n, comma, p, and tell it true to find a cumulative probability. And then I'm going to take 1 minus the probability I just found. And notice this 0.321, that's a higher probability than the example we just did. It's more likely that you're going to get 3 or more than it would be to get 4 or more. That's the one we just found. More than 3 meant 4 or more. So here I've got this probability. Let's take a look at another example. Let's find the probability of guessing between 1 and 4 questions correctly inclusive. That means including getting 1 or 4 right. And here this graph is showing exactly what I'm trying to find. The probability of getting 1, 2, 3, or 4 questions correct. In order to find this probability, I need to turn it around and write it in terms of probabilities to the left. In other words, what I'm trying to find is the probability of getting 4, 3, 2, 1, 0, that's this graph, minus the probability of just the 0 bar. So what I'm going to do is use 2 CDF probabilities and subtract them. I've set this up in a 2-column format to make that easier. Here in this column, I've got the case of k equaling 4, that's this graph. And here in this column, I've got the scenario where k is equal to 0. That's this graph. Other than that, I'm going to type in pretty much the same formula I've been using. Binomial dist of k, comma, n, comma, p, comma, true. Now, because I've got these lined up, I can just use copy and paste. Let's copy and paste that over there, and I get my result for the 0 case. And finally, to get the final probability, I'm going to take, notice the less than or equal to 4 minus the less than or equal to 0. I'm going to take that probability and subtract the 0.1. And 0.873 is the probability that I get 1, 2, 3, or 4 questions right in my guesses. That's this red shaded area that I see here. I'm going to take a look at one last example, but I'm going to do this one a little more quickly because it's very similar to what we just did. Let's find the probability of guessing between 1 and 4 questions correctly exclusive. In other words, excluding the 1 and the 4. So if I set this up with strict inequalities instead of the inclusive inequalities, well, I need to rewrite it in terms of inclusive inequalities. So between 1 and 4 means getting either 2 right or 3 right. Once I've rewritten it like this, it's the exact same type of problem as I worked up here, except now it's the probability that x is less than or equal to 3 minus x less than or equal to 1. The work is now identical to what we just did up here, except we're using different values of k. I've got that worked out here. Same formulas. If you take a look at this, binomial distribution, and this formula, binomial distribution there. And so when I subtract them, I get this result. Here's a quick way that I could check this result. I have a probability of 0.519. That should be the sum of the values of 2 and 3 in the distribution we had at the very beginning of the video. So let's take a look back up there. If I add the values for 2 and 3, it does look like I'll get about 0.518, 0.519, same thing, but for rounding. And that is our end result.